stop and wonder what makes a lemon so sour? Or how does soap actually get a greasy pan clean? Well, the answer is this hidden chemical world that's, believe it or not, all around us and even inside us. So today we're going to dive into acids and bases, these invisible forces that pretty much shape our lives. I mean, think about it. Heartburn after a huge meal, a stubborn curry stain that just won't come out. The solution to both of those isn't some kind of magic, it's just straight up chemistry. These everyday annoyances, they are perfect examples of acids and bases at work. So let's pull back the curtain and see exactly how this stuff happens. Okay, so here's the game plan. First, we're going to cover the basics, acids and bases 101. Then, we'll get into how they reveal themselves with these cool color changes. After that, we'll see what happens when they actually react with each other, figure out how to measure their strength, and finally, we'll tie it all together and see why any of this chemistry really matters in your world. All right, let's jump right in with Section 1, Acids and Bases 101. It's time to meet the two main characters of our story today. These are the absolute fundamental building blocks of the chemical world. So, what are the classic telltale signs? Well, acids, think lemon juice or vinegar, they have that sour taste. Bases, on the other hand, tend to be bitter. But, and this is a big but, we obviously don't go around tasting random chemicals, right? That's a terrible idea. So, chemists use this special tool called litmus paper. It's super simple. Acids turn it red, bases turn it blue. Think of it like their chemical fingerprint. And that litmus paper? It's a perfect example of what we call an indicator. I like to think of it as a little chemical detective. It's basically any substance that changes color when it meets an acid or a base, giving us this really clear visual signal. And again, absolutely no tasting required. Okay, on to Section 2, the telltale color change. And this is where it gets really cool, because it turns out litmus paper is just the beginning. Chemists, and even nature itself, use all sorts of amazing, colorful clues to figure out what's what. And what's so wild is that you probably have some of these in your home right now. I mean, litmus actually comes from a plant, a lichen, but turmeric from your spice rack, red cabbage leaves from the fridge, even petals from flowers like hydrangeas or petunias, they can all act as natural indicators. How cool is that? Okay, here's a perfect real-world example for you. Remember that stubborn curry stain we talked about? Well, the turmeric in the curry is the natural indicator. So when you scrub it with soap, which is a base, the stain turns that reddish-brown color. The stain is literally telling you about the chemistry of the soap you're using. Mind-blowing, right? But it's not just about what you can see. Chemistry uses our other senses too. Get this, there are also things called olfactory indicators. These are substances that change their smell depending on if they're in an acidic or basic environment. So things like onions or clove oil, they have that really distinct smell that can be completely changed or even totally wiped out by acids and bases. All right, so now we know how to identify acids and bases. It's time for the main event. Section 3 is all about what happens when chemicals react. Let's dive into the fundamental rules of engagement for when these things actually meet. First up, we've got a real classic. What happens when you mix an acid with a metal? This is one of those fundamental reactions you'd see in pretty much any chemistry lab. And you can see it right here. When these little bits of zinc metal are dropped into sulfuric acid, you immediately see all these bubbles forming on the surface. Now that's not just some random fizzing, that's a full-on chemical reaction producing a totally new substance, hydrogen gas. And this reaction always follows a predictable formula. You take an acid, you add a metal, and you get a salt plus hydrogen gas. Now, quick note, when a chemist says salt, they aren't just talking about the stuff you put on your fries. It's a whole category of compounds that are formed when the metal basically boots out the hydrogen in the acid and takes its place. Okay, for our next reaction, let's switch it up a bit. What happens when an acid meets a metal carbonate? And you know these. We're talking about things like chalk, limestone, even marble. They're all basically calcium carbonate. This time, the result is a little different. Yes, we still get a salt and some water, but instead of hydrogen gas, we get carbon dioxide gas. This is the reason for that intense fizzing you see when acid hits limestone. It's just releasing a ton of CO2. But maybe the most important reaction of all is what happens when an acid and a base finally meet face to face. This is called neutralization, and it's like a perfect chemical balancing act where the two substances completely cancel each other out, just nullifying each other's effects. And the formula is so simple and elegant. A base plus an acid gives you a salt and plain old water.
That's it. Remember that heartburn we talked about? When you've got too much stomach acid and you pop an antacid tablet, which is a base, you are literally performing a neutralization reaction right inside your own stomach.
So all of this leads to a really important question, which brings us to our fourth section, introducing the pH scale. The easiest way to think about this is like a ruler, but for measuring chemical strength.
I mean, just think about it for a second. The hydrochloric acid in your stomach is incredibly powerful, right? But the citric acid in a lemon is something you can actually eat. So clearly, not all acids are created equal. So how in the world do we measure that huge difference in strength?
Well, we do it with something called the pH scale. Fun fact, the P actually stands for potence, which is German for power. It's a simple scale that runs from 0 to 14, and it measures the concentration of hydrogen ions. Right in the middle, 7 is neutral. Think pure water. Anything below 7 is an acid, and the lower the number, the stronger it is. Anything above 7 is a base, sometimes called alkaline, and the higher the number, the stronger it is. So what does strength really mean in this context? Well, it's all about these things called hydrogen ions, or H+ ions. It's pretty straightforward. When they're dissolved in water, strong acids release a ton of hydrogen ions. Weak acids, they only release a few. That is the fundamental difference, and that's exactly what the pH scale is measuring.
And that brings us to our final section, chemistry in your world. This is where we bring it all home, connecting everything back to our daily lives and seeing why understanding pH is just so critical for all of us.
You see, the balance of pH is absolutely vital for life. It's not an exaggeration. Our bodies have to maintain our blood pH in this razor-thin range between 7.0 and 7.8, just to survive. In the environment, acid rain, with a pH below 5.6 can devastate aquatic life. And it all comes back to us. Our own stomachs use powerful acid for digestion, and even the plants that grow our food require a very specific soil pH to thrive. Which leaves us with one final, kind of mind-bending thought. We've just seen how life here on Earth depends on this incredibly delicate pH balance. But then you look at a planet like Venus. Its atmosphere is made of thick, swirling clouds of sulfuric acid. So, knowing what we now know about pH, what does that tell us about the possibility of life on other planets? It's a huge question, and it really shows just how universal and how absolutely vital this hidden chemistry truly is.